Hello, my name is Benjamin Branstetter, and today I'll be going over Physics 2212, Lab number 2, Charged Tape Revisited. So, what was the purpose of this lab? Well, the purpose was to use old models of charged tape as point charges to test whether modeling the tape as distributed charges would be more accurate. What models and fundamental physical principles did we use? Well, we used the tape to model distributed charges by assuming that the charges had been equally distributed across the surface of the tape, so that we can use Coulomb's law. And then we used Newton's second law, F equals ma, and in this case, F equals mg, along with Coulomb's law, which we use multiple times for the different charges, to calculate the charge on each piece of tape and the electric and gravitational force on the pieces of tape. And then we use the principle of superposition, which is essentially just that electric fields and forces add vertically. And we also use the principle of static equilibrium, which explains that the electric force is equal to the force of gravity in this case. So what's a basic view of our results? Well, initially, the force of gravity and the force of electric force were not equal when we used our initial charge guess from the first experiment. Which meant that I needed to adjust the estimate, and in the end, it ended up being about double its original value, which is when we found that the force of the electric force and the force of gravity were equal. So initially it was 1.4 times 10 to the negative 8th coulombs, and in the end it ended up being 2.9 times 10 to the negative 8th coulombs, was where they're about equal. So what assumptions and models did we use? Well, one assumption we used was that both pieces of tape attain the same amount of charge from their interaction. The second was that all of the charge on both pieces of tape is distributed evenly across the surface of the tape. The third was that none of the charge is transferred to the person holding the tape or its surroundings. And then the fourth was that air resistance is negligible. And then the models was basically just that the pieces of tape were assumed to have equally spread charge across their surface, and they were assumed to have total equal charge. So the experiment, the system was the three pieces of tape that we used, and then the surroundings is everything else in the universe. The initial conditions were that the two pieces of tape were stuck together while another spanned across two standing markers. And the procedure was essentially just that we spanned one piece across two markers, and then we attached two pieces together and quickly removed one. We basically just held that quickly removed piece under the piece that spanned the two markers, and then measured how far apart they repelled each other. And then that allowed us to find R, and then eventually find the charges on the pieces of tape, because we assumed that the charges were equal. So this was the main portion, was the code. Basically, we just used the code and physical data from the first experiment to calculate the electric field, and then we applied this to an electric field across the surface of each piece of tape, which was determined by a number of factors, including how many charges we assumed were spread across the tape. In this case, I used 10. After doing that, we can find the force that each piece of tape exerts on the other, and this allows us to compare the force of the electric fields and the force of gravity. So here's just another piece of the code portion that we did, which is essentially just setting up the visualization of the actual experiment, which includes the number of charges that I used. Here I used n equals 10, which is number of charges, and then basically just how we set up the actual arrows and the graphics that you'll see later. So how close were the results? Well, the computational model shows just how much assumption can affect experimentation results. Assuming that the charges on the piece of tape were point charges in the original lab, resulted in us finding a charge that was half the value measured when we assumed that there were n charges spread across the tape, which is more accurate to real life. In the end, we found that the electric force on the tape was about 2.0 times 10 to the negative third newtons, and the force of gravity was about 1.96 times 10 to the negative third newtons. These results are very encouraging because that means that our static equilibrium is basically right, with the exception of a few sources of error. So what were some of those sources of error? Well, the charge on each piece of tape may not have been equal. Some of the charge may have been lost due to contact with the person holding it or the surroundings. And then it's unlikely, but the temperature of the room may have affected how the charge was distributed. So for the what if and why questions, compare the estimated value of the charge with the experimental data. So the estimated charge of our first model was 1.4 times 10 to the negative 8 coulombs, and in our experimental model, it was 2.9 times 10 to the negative 8 coulombs. The largest reason for this discrepancy is essentially just that in the first we assumed that the charges were point charges, and now we assume that they are distributed, which has a big effect on how the balancing force is spread across the piece of tape. And then why do they differ? Basically, as I mentioned before, it's that the models that we used are different. The charge remains in one place initially, which reduces the amount of force spread across the tape. But in this case, the force is spread across the whole length of the tape, and we know that force decreases with distance, which is basically 1 over r squared. And then the conclusions are just that the lab showed us that the distributive model was actually more accurate than the initial model that we used. Thank you.